Hello, welcome everybody to our second to last webinar for the Volcanic Systems Modeling Workshop. We have two speakers today again, and then on Thursday at the same time, 12 Central, two more speakers. And that will conclude the webinars for this workshop. And on Friday of this week, 7th of May, from 12 to 2:30 Central, we have our final planning meeting. The focus will be discussion of what's going to be in the report, review what we have thus far, and so forth. So anybody is welcome to attend the planning meeting. If you have any questions about that, feel free to send an email to Kyle and I. Our contact information is on the workshop webpage. To participate in the workshop, you have to register separately. And the link for that is also on the webpage. And with that, I give it to Kyle.
So our first speaker today is Hélène Le Mével. She got her master's in geophysics from IPGP in Paris and a PhD in geophysics from the University of Wisconsin-Madison in 2016. She's been a staff scientist at the Carnegie Institution for Science at the Earth and Planets Lab since 2017. Her research uses field and satellite geodetic data and numerical models to study magmatic processes leading to volcanic unrest. Her talk today is modeling volcano deformation. Hélène?
All right. Here we go. Thank you, Kyle, and thanks, Helge, for organizing this workshop and for inviting me to give this talk. So today I'm going to give an overview of volcano deformation modeling. I will show you what are the different approaches and some of the different tools that exist to model deformation measured at volcanoes. And we'll see what we can learn from them in terms of magmatic processes. Okay, here's an overview of the talk. First, I'll give a brief introduction and present some simple analytical models. Then in the first part, I will focus on modeling the host rock around magma reservoirs. We'll look at different parameters that affect the crustal deformation. In the second part, I'll focus on modeling the magma reservoir itself. And again, I'll show a variety of examples and highlight some important contributions. And finally, in the last part, I'll talk a bit more about integrating various data sets to deformation models and about future challenges and perspectives for modeling. So volcanoes deform due to pressure changes taking place underground in the crust. We will see that there are a variety of processes that can generate ground deformation at volcanoes. And as you probably know, surface deformation can be measured either by satellites or using instrumentation on the ground, for example, GPS, INSAR, tilt meters, or strain meters. On the right is a very recent example of surface deformation measured by INSAR over, so this is an interferogram showing 1 week of deformation in March of this year due to the magma accumulation in the crust under the Reykjanes Peninsula in Iceland. So there we were able to follow the dike path for several weeks before it finally made it to the surface and the ongoing eruption started. So surface deformation data are very useful to investigate magma storage and transport pathways under volcanoes. And that's why measurement of volcano deformation is one of the 3 main data sets used for volcano monitoring, together with seismicity and gas measurements. So in order to interpret those deformation signals in terms of magmatic processes, we use modeling. The main goal is to determine what is the dominant physical process governing the surface deformation. And we want to determine what is the status of the magma reservoir. So let's look at what type of deformation we can expect at different stages of what we call the volcanic cycle. So a typical cycle for a stratovolcano is sketched here. We see that during the pre-eruptive stage, there is a magma reservoir pressurization. creating inflation. If pressure in the reservoir exceeds crustal strength, we'll usually have an eruption and sudden deflation of the edifice due to magma being removed. Following the co-eruptive interval, we would measure slow deflation until we are back to steady state during the intereruptive period. On the side there, I listed some examples of processes that could create surface deformation during each of the 3 stages. So the first thing to note is the deformation created by all of those processes actually superimpose and create much more complex spatial and temporal patterns of deformation rather than simply inflation followed by deflation. So for example, pre-eruptive deformation could be due to the influx of new magma, but also to a dike intrusion or volatile solution. And while the volcano is erupting, the magma chamber might be at the same time refilling from a deeper source, for example. The second point is that a lot of volcanoes have a hydrothermal system, usually above the magma reservoir, sketched here in blue. And the variations of pore pressure within this hydrothermal system can also create similar patterns of deformation. And finally, not all episodes of inflation are followed by an eruptive episode, which is why there's this gray arrow here going directly from inflation to deflation. So this illustrates the different challenges in interpreting surface deformation with the goal of forecasting the volcanic activity. So by definition, models are simplified representations of reality. So in order to model the surface deformation measured at volcanoes, we must make different simplifying assumptions on the crustal rheology. So how does the crust behave when it's subject to stress? We must assume the source geometry and determine the magma properties if we are modeling magma dynamics. And finally, we must make assumptions on the dominant process or the one of interest for our study so that we are able to choose the appropriate physics to model this process. For a given mathematical model, we can have an analytical solution, which provides exact closed form equations, or a numerical solution, which is an approximation of the solution based on a set of boundary and initial conditions and using different discretization method and numerical methods. So in this talk, I will talk a lot of the examples will be using the finite element method, which allows us to use arbitrary geometries and distributions of material properties. Okay, so to start with, let's look at some simple analytical solutions for deformation due to sources of simple shape buried at depth. Those are widely used in volcano geodesy to estimate some key source parameters: the location and the geometry of the source and the strength of the source, so either a pressure or a volume change. On the right, we see 3 different types of sources: the pressure point source solution from Mogi, the pressurized spheroid solution from Young, and the Okada solution, which models tensile cracks and can be used to model dikes or seals by prescribing a uniform opening on the surface. Another solution proposed by Niku and other is the compound dislocation model. So it uses 3 orthogonal rectangular dislocations to approximate both the planar and the volumetric sources. We can see that the pattern of vertical and horizontal displacement created at the surface are different for each of those sources. So the first row is the vertical displacement, second row is horizontal displacement. So we are able to distinguish between those simple geometries based on the observed surface displacement. Something to note is that there's always a trade-off between the estimated depth and the strength of the source. So we can only try to mitigate this trade-off using other information. So the models I just showed assume that the expansion source is buried in a homogeneous, isotropic, and elastic half space. So it means, as shown on this sketch here, that the lateral and the depth boundaries extend to infinity, There's no topography, no layering or spatial variations of crustal elastic parameters. For the pressurized sphere, such as the MOGI model, it's also important to note that it's only applicable if the depth is much greater than the source radius. So if we summarize the pros and cons of those simple analytical models, the main advantage is the simplicity of the formulation. So it makes the calculation fast and it's easy to integrate in an inverse problem. For example, using least square, we can estimate the best fit parameters easily. They are good to determine the best fit geometry, and it can hint at the type of underlying process. For example, whether the best fit is a pressure source or a dislocation, if it's elongated or dipped. So in the end, they are very useful as a first order approximation. They could also be used as a first step before using more complex models. Now, the main limitations are related to those underlying assumptions. So the main one is the highly simplified source geometry and idealized crust that it doesn't allow to consider variations in crustal parameters or include other data sets or multiple sources. And second is that those models are purely kinematic, so they do not consider the dynamic process that leads to the change in pressure. So they cannot be used to predict the evolution of the deformation with time, and they can't really be used to assess the eruption potential at a volcano. Okay, so in this first section, we will focus on modeling the crust, but not as an elastic half space. We'll look at a few examples of modeling studies and see what are the important effects to consider when modeling the host rock deformation around magma reservoirs. And first, let's look at the impact of mechanical heterogeneities. We know that the crust is most likely not homogeneous, especially in volcanic areas. And the specific distribution of material properties is really what's going to control how the stress applied to the chamber walls translates to the surface deformation. So one way to know about those heterogeneities is to use material properties derived from seismic tomography. The first example here on the left from Ronchin and others is looking at unrest at Rabaul caldera in Papua New Guinea, using a 3D FEM model. And there you have different geological blocks with different material properties. For example, in gray is the intra-caldera fill. It has a much lower density sediments, and so a lower Young's modulus and Poisson's ratio. And here on the right, the second example is from Masterlag and others, modeling deformation at Okmok volcano in Alaska. And both of them show that using seismically derived material properties, not only it improves the fit to the data, but it significantly influences the parameter estimates. Specifically, the source depth is underestimated by homogeneous models, and it also affects the estimate of the source strength. So it's especially important to consider the weak layer of material at calderas, which is often present, as this weak material, it accentuates the deformation. Here I have other references if you're interested in more heterogeneous models and, for example, application to Kempe-Flegery. Now let's look at the effect of host rock fracturing on deformation sources. So the elastic continuum approach that is used in the simple analytical models only works for small displacement and small strain. So it's usually the case during volcano inflation. But during volcano deflation episodes, the strain can be quite large actually, and sometimes it leads to caldera collapse. So in this study by Holohan and others, they look at the episode of deflation experienced by Piton Lafournaise in Reunion in 2007. What they find is very interesting is that using typical elastic, continuum-based elastic modeling, the estimated source depth becomes shallower with time, and the shape also changed with time. So on the middle figure, we see the 3 stages of deflation, with fracturing that develops first around the magma body and then towards the surface. For each period, the optimal elastic deformation source is shown as this dashed ellipse. So we see that it was estimated to become shallower with time. So it's something to keep in mind when interpreting results from linear elastic models, is that the best fit source represent the magma body, but it can also be a zone of inelastic host rock deformation around and above the body. So in that example, it could lead to the wrong interpretation that magma was ascending towards the surface, where actually a ring fault where a structure was being formed following the eruption of magma on the side, on the flank. The challenge here is that for non-continuum mechanics, to simulate the growth of fractures, we need to use different numerical methods. Here, in that case, they used a distinct element method and a bonded particle flow. So far, the crust was considered to behave elastically. When a stress is applied, there is an instantaneous deformation of the material, and stress and strain were linearly proportional. It has been shown that the viscoelastic rheology is more appropriate to model rocks around long-lived magma chambers, since rocks are heated beyond the brittle ductile transition. So some models were developed that include a region around the chamber with a viscoelastic rheology, also called a viscoelastic shell. So it means in addition to the recoverable strain following the application of stress, there is a permanent and time-dependent strain. So here's an example of a 2D FEM model to simulate deformation observed at Long Valley caldera during non-eruptive unrest from Newman and others. And the main effect of adding this time-dependent deformation is that compared to a purely elastic model, the viscoelastic shell creates more displacement. So the pressure required to reproduce the observed surface displacement is going to be much lower. Here, purely elastic models needed very high and unrealistic pressure change, actually higher than the lithostatic load. So here is the example of a viscoelastic time series for different viscosity of the shell. The relaxation time that controls this temporal evolution of deformation, it depends on the chosen crustal viscosity around the source and the rigidity or the shear modulus. So to conclude, in a viscoelastic model, the deformation over a given time interval is not always an indication of a new magma flux. So it's a combination of magma flux and the transient viscoelastic response. And this has very important implications for the assessment of magma budgets over an entire eruption cycle. So choosing the viscosity of the crust can be challenging, since it can span several orders of magnitude, and also the choice of the size of the viscoelastic shell can be a bit arbitrary. So when we do not have specific constraints on the crustal structure, the best is to derive the viscosity distribution from thermal models. We can simulate the heat source by setting a constant temperature at the chamber wall and solve for heat conduction in the crust to obtain the temperature distribution. And finally, we can convert this temperature distribution into a viscosity distribution. So this approach is used, for example, in Del Negro and others to model deformation at Etna volcano. Here on the left, you see two different viscosity distribution based on two different chamber wall temperatures. And on the right, I show an example of viscosity and temperature distribution from Greg and others from a study on the triggering of caldera-forming eruptions. So the next couple of slides, I will show two other examples of studies that use 3D thermo-mechanical models to model deformation. So one of the great advantages in using 3D thermo-mechanical numerical models that include realistic rheology and topography, is that we can assess the stress evolution in the host rock. And this can help us determine the likelihood for failure. So using more Coulomb criteria for failure, we can determine the location and type of faults expected to be generated in the roof of the magma chamber due to overpressure. So it's really important when studying the potential trigger for eruption. So for example, Greg and others in 2012 studied the triggering of caldera-forming eruptions and found that one of the primary control was the roof aspect ratio. Since the effect of having a ductile region around the chamber is to buffer the reservoir pressurization, it actually delays the failure. So using elastic models, we wouldn't get the same results. This other study here is another example from Greg and others in 2018, where we look at the stress state and the stability of the magma reservoir at Sierra Negra during the 92-95 inflation. And we found that the host rock surrounding the Sierra Negra reservoir actually remained in compression with very little change in overpressure right up to the eruption in 2005. So there was no tensile failure until we consider the stress transfer from an external trigger. In that case, it was an earthquake that happened a few hours prior to the eruption that was needed to trigger the 2005 eruption. So finally, another important consideration is the influence of tectonic stresses on deformation models of magma chamber. So Cavanis and others use the same kind of 3D FEM thermo-mechanical models, but this time they look at reservoir stability. At Taupo in New Zealand, they look at the stability under different tectonic regime, either extensive or compressive stress. So the stability of the reservoir is assessed using the Moore-Coulomb failure criterion. And the main results show that the regional extension decreases the stability of the roof, and it promotes the onset of caldera collapse. So the takeaway message here that I want to point is it's very critical to include local and regional tectonic stresses in numerical models in order to determine the potential for failure. And then we can also get a sense of the repose time intervals between eruptions. And we can compare this to, for example, melt accumulation timescales obtained from geochemistry. To summarize this part on modeling the crust, we can say that all of these parameters, so the non-elastic rheologies, heterogeneities in the crust, tectonic stresses, are all very important to model in order to accurately determine the source of volcano deformation. And to model those complexities, 3D numerical approaches are often necessary. And then using these models, we can calculate the 4D stress evolution in the rocks surrounding the magma chamber and study mechanisms of failure. So this is more informative than the elastic half-space models, and these results can actually help forecasting future eruptions. Okay, so we looked at the deformation of the crust around magma reservoirs. And in this part now, we'll take a look at what happens in the magma reservoir itself, how to model it. And in the models we looked so far, the magma reservoir experiences a pressure change or volume change, but the magma that feeds the reservoir and pressurizes the reservoir is not actually modeled. If we assume a flow of Newtonian incompressible fluid through a cylindrical pipe, then the flow rate between the inlet and the outlet of this pipe, so between here and here, named Q here, is proportional to the difference in pressure between the 2 points to the conduit radius and inversely proportional to the fluid viscosity. So it is possible to derive some analytical solutions for the reservoir pressure evolution in each of the chamber following pipe flow for different inlet pressure histories and for simple reservoir geometries. So this example here, for example, in Reverso and others, in 2014, they considered the case of two fluid-filled magma chambers with a constant inflow of magma at the base of the deep chamber. And they applied this model to explain the post-eruptive inflation at Grímsvötn in Iceland. To explain the changes in deformation, deformation rates observed at Laguna del Maule volcano in Chile, we derived an analytical solution for a single spherical reservoir and an ellipsoidal reservoir in an elastic crust being fed, but this time with an increasing mass flow. And we can also solve the same problem, but numerically. So this time we will solve for Navier-Stokes equations in the conduit and in the reservoir, and couple the fluid pressure to the crustal deformation. Using the numerical approach allows us to consider more complex rheology and, for example, viscoelastic crust. So using the 3D numerical model for magma injection into an ellipsoidal chamber located in a viscoelastic crust, we were able to reproduce the increasing and decreasing uplift rates that were measured at Laguna del Maule since 2007. So on the right is the uplift time series. That's the model result after adjusting the model parameters. And on the left, we see the adjusted conduit inlet pressure history and reservoir overpressure. And here at the bottom, the corresponding flow rate and total volume change. So this model provides a physical explanation for the changes in deformation rates that we observe on the time series, but it also provides interesting constraints on some parameters that are the conduit radius and the effective magma viscosity. So the magma injection model, as I said, it assumes a fluid-filled reservoir and a fluid-filled pipe. Instead of considering the magma chamber as an isolated body of melt that is surrounded by crust, an alternative is to describe it as a porous domain, and the pores would be filled by melt. We can then use the theory of poroelasticity to describe the deformation of this reservoir. So now the reservoir is just a mush region in the crust, characterized by porosity, melt fraction, and permeability. So the analytical models I show here were introduced by Liao and others in 2018 and 21. And it considers the mechanical response of a magma chamber with poroelastic or poroviscoelastic crystal mush around it. So in this model, on the sketch here, this is from 2021, there's a liquid core of fluid and compressible magma in a spherical reservoir and a shell of poroviscoelastic material around it. And then an injection of magma is simulated in the liquid core, and magma is allowed to flow across the liquid mush interface and throughout the mush. So the flow is driven by the gradient of pore pressure and governed by Darcy's law and the mass conservation equations. So those models showed that the time-dependent response of a poroviscoelastic magma chamber is governed by two timescales. So the poroelastic diffusion timescale and the viscoelastic relaxation timescale. The short-term evolution of the magma mush system is dominated by the poroelastic diffusion timescale. So that will be the important one to interpret the surface deformation, since the surface deformation happens over usually less than a year or few years. Okay, so we can easily imagine that considering the role of mush in the deformation of magma reservoir is very important for magmatic systems with lots of crystals, such as long-lived reservoirs, at calderas, for example. But this framework can also be applied to any reservoir, really, by adjusting permeability and porosity of the different regions that make up the system. Okay, so we are working on pursuing this work and extending the applications of these models using numerical FEM model to be able to have more complex crustal rheologies and magma chamber geometries. Another category of models that look at the processes happening in the conduit, but this time between the reservoir and the surface, are the physics-based models, such as the studies from Kyle Henderson and Paul Segal and Yinki Wong and Segal. So although this is a 1D time-dependent model, the magma contains crystals and bubbles, and both viscous flow and plug flow are solved for. And this model is applied to effusive silicic eruptions, for example, 2004-2008 eruption of Mount St. Helens. And it is used to predict 3 different time series: the extruded volume, the CO2 emission, and the ground deformation. So I won't go into any more details because Paul will talk about it more later this week. The point here is that these physics-based models allow to model very key time-dependent processes, such as the gas exsolution in the conduit, and to explain the temporal evolution of different surface observations. So they do have the potential for predicting the evolution of the system. Finally, there are also several numerical models solving for magma mixing and convection in magma chambers. And this is just one example showing a multiphase magma model that look at the replenishment of a long-lived magma reservoir by more primitive magma coming from depth. And this is a key process since we invoke it a lot of time to explain most of the uplift episodes, especially at calderas. This is a 2D FEM model that solves for mass, momentum, and energy equations for a gas, liquid, and crystal mixture. So different simulations were run with different incoming magma properties, varying the CO2 and H2O content and the magma density. This study is really modeling an n-member case where the convection would be purely driven by the buoyancy. And the two magmas with 2 different densities mix. And what the results show is that the arrival of magma in the shallow chamber, if the buoyancy force dominates, actually lead to a decrease in pressure in the upper chamber. So this is actually a 2-chamber system with a much deeper chamber. This model reveals very complex patterns of reservoir pressurization that really cannot be explored if we do not consider the multi-phase rheology of the magma. So the next step would be to couple this type of model of magma mixing and convection to a crustal model to solve for the host rock deformation. So to summarize, the magma dynamics, both in the conduit and in the reservoir, are very important. Very important to explain the complex patterns of surface deformation that we observe at the surface. And the physics-based models and the multi-phase numerical models allow coupling the magma dynamics to the mechanical response of the crust. So we can learn a lot more from them than from the elastic half-space models. So to conclude, I'll talk a bit more about some of the challenges and perspectives for future modeling studies. One of the main challenges is to integrate different data sets. So many deformation modeling studies already integrate data from different sources. For example, we can take advantage of the spatial resolution of INSAR and the higher temporal resolution we get from GPS data. But for volcanoes that are well monitored, there's no reason not to use other data sets to calibrate our models. For example, we can combine INSAR, GPS, and seismicity, like in this study of the Bardabunga dike intrusion that happened in Iceland in 2014. And there, the combination of seismicity and deformation the modeling of the deformation really helps to map very precisely the temporal changes in the dike geometry and the pressure changes in the dike. And thanks to the seismicity, we could understand better the tectonic stresses that govern the path taken by the dike. Another very powerful combination of data set is the joint modeling of deformation and gravity changes. And finally, we can combine gas geochemistry with deformation, as done in this modeling framework proposed by Kilbride and others in 2016. So in this study, it's basically a compilation of ground deformation, SO2 emission, and erupted volumes for 26 volcanic eruptions. And they look at pre-eruptive magma conditions. So they define this ratio R, which is the ratio of erupted volume divided by the measured volume change from geodetic modeling. And when we plot the sulfur yield, so essentially the R is proportional to the magma compressibility. If you look at the sulfur emission, the sulfur mass versus the ratio, you can see that there are different trends. So they are defining different trends, and they provide constraints on two main very important parameters, which is the magma reservoir depth and the volatile content for each of these eruptions. The caveat is that this approach is mostly applicable to study explosive eruptions, for which we do have SO2 emission data, usually from remote sensing, and erupted volumes at the surface, and also some model deformation to get the volume change from geodesy. So if we summarize the main challenges for modeling volcano deformation, first, we need more studies that integrate multiple geophysical and geochemical data sets to calibrate the models of volcano deformation. These will help us discriminate between the driving mechanisms that we wouldn't be able to distinguish only based on their geodetic response. Second, we need to keep working on integrating magma dynamics into mechanical models of volcano deformation. So linking the more realistic crustal models we saw in part 1 to more physical processes happening in the reservoir and in the conduit that we saw in the second part. And the third point is that a remaining challenge is to be able to determine the evolution of a reservoir leading up to an eruption. So for that, we need to figure out how to use each of these model advances for forecasting eruptions. And that will actually be the subject of the next talk. The last slide here, I illustrate some perspective for the talk that we can talk about for the modeling collaboratory. The fact that a lot of past and current studies focused on modeling one physical process, for example, magma intrusion, usually using one calibration data set, for example, displacement, at one specific volcano, and usually over one eruptive episode. And we have made a lot of progress in understanding some of the mechanisms driving deformation using these studies. The goal for the future might be to move towards more modeling studies that consider either several physical processes or using several calibration data sets, maybe explaining the behavior of several volcanoes or considering several eruptive episodes from the same volcano. Of course, we won't be able to have a single model that includes all the complexities needed to model all the deformation patterns observed at all volcanoes. So I think this is one of the topics we'll discuss more later this week on Thursday and Friday. So I'll stop here and thank you for your attention.
Thank you, Hélène. Dear participants, if you would like to ask a question, use the Q&A functionality at the bottom of your Zoom window.
I do have a couple of questions. First question so far is from Sahan Hajimirza. I apologize if I mispronounced your name. The question is, can surface deformation characterize overpressure, in parentheses, stress, in conduits?
Okay, so now we're talking about the deformation of the conduit. So can surface deformation characterize solely, you mean only the deformation of the conduit, or the
Hi, Helen. Great talk. So what I meant was the source of overpressure has always been considered, most of the time is considered in magma reservoirs. Can a source of overpressure in conduit also cause surface deformation?
I think, okay, so I think that what happens is that what happens in the conduit is it happens over a very short time scale, but I think there is some deformation associated to conduit deformation, and the process is happening in the conduit, but I'm not sure if there are a lot of studies actually looking at specifically not the overpressure from the reservoir, but the deformation of the conduits right before the eruption. But probably Paul might be able to answer this question more.
Okay, so we have the next question from Marco Knuver.
Hold on a second. Paul, did you want to follow up to Hélène?
Well, there are some rudimentary models for pressurization of conduits, and also, in fact, shear tractions applied to conduit walls. The general rule is that you have to be pretty close to the eruptive vent to see these effects. You don't tend to see them in the far field.
Okay, so the next question comes from Marco Knuver. He says, great talk. Did you consider the parentheses chemical and mechanical interaction of magma and host rock at magma chamber level and or in the conduit? And how does that influence magma ascent? There should be changes in the dimensions of the chamber/conduit as well as rheological changes. Are there models to account for that?
Right. Yeah, so now we're talking about changes, yes, in dimension of the chamber or even in the conduit during during periods of activity. So I think what he means is talking about the damage that is evolving with time. And I think there are some models being developed. Some different groups are working on damage models, and the effect mostly is going to be on, like he suggested, changes in the elastic properties of the crust with time. So basically, the stiffness is going to be reduced. So the youngest modulus could decrease with time. Yes, there are some studies, and yes, it does influence the deformation pattern that we observe at the surface.
Great. The next question is from Delphine Smitarello about the Laguna de Mole deformation. You show that your model adjusts very well to the GPS time series. Do you have GPS in another location at this location or INSAR time series, and how does it behave? And then, is your analytical model able to fit also the spatial complexity of deformation?
Yeah, so the time series I showed was indeed from one GPS site closest to the maximum uplift. We do have other GPS sites, 5, and this is actually the INSAR and GPS was inverted at the same time for using the numerical models. And this ellipsoid I showed was the pipe flow going to feed the ellipsoid. This was explaining, this was reproducing both the temporal pattern and the spatial pattern using both INSAR and GPS.
Okay, so the next talk comes from Chuck Connor. He says, nice talk. Do you expect volcanic deformation to be different in a new or young volcanic arc compared to an old volcanic arc? That is, how does the history of the crust on scale of millions of years affect magma injection and deformation response, if at all?
Wow, that's a very broad question. So I don't think some studies have been specifically done on like the age of the arc, but I think it's about how the magma chamber at the volcano we're looking at has been replenished. So are we looking at a mostly cooling system? And so the difference is going to be on the structure of the crust and how hot it is, and what magma flux is feeding these volcanoes. So yeah, I guess there are a lot of parameters that play, like the thickness of the crust, the magma flux, as I said, and the heat. So I cannot say right now like how the age of the arc would influence the response to the deformation.
All right, great. Thanks, Helen. Unfortunately, I think we need to move on at this time just to get Grace's talk in. There are some questions remaining in the chat box. Our speakers may, I guess, at their discretion, follow up with you individually, either in the chat box or via email later if they'd like to answer your questions. Thanks, everyone, for the great questions, though, and Helen for the great talk.
Thanks.
So our next speaker today is Grace Bato. Grace completed her PhD in 2018 at ISTER in France, and she's currently a postdoc at JPL Caltech. Her research interests have been mostly focused on volcano geodesy, developing frameworks to track and forecast the state of volcanic systems in near real time. She does this by combining process-based dynamical models with large amounts of data. Her talk today is towards better model data fusion frameworks, data assimilation for volcano applications. Grace?
You see my slide?
Okay, it's there.
Yeah, there you go. Should I start? Hi everyone. So I hope you can hear me, and I hope you're all staying healthy and are hanging in there. So first, I'd like to thank Kyle and Helga for organizing this series of seminars. I actually enjoy them a lot, and it's quite sad that we are now nearing the end of this season. I'm looking forward to having a season 2 of this seminar series and to have or continue the discussion on this modeling laboratory. So for this talk, I thought I would give a data assimilation introduction and show some demonstrations or applications where sequential data assimilation can actually be useful for this modeling laboratory. So I will start by assuming that we all agree here that as scientists, we want to uncover the truth about this system of, about our system of interest, and basically what are the mechanisms that drive our dynamic system, what causes transient events. For volcano scientists like us, we often ask fundamental questions like what drives eruptions? Will an eruption occur, or will it just be an intrusion, and so on and so forth. So typically, to obtain information about the true state of the system, what we do is we develop or use instruments or observing systems to measure it. However, the true state of the system is continuous both spatially and temporally, but the observations or the data that we measure are actually just snapshots of the true state of the system. Observations are sparse, both spatially and temporally, or discrete in space and in time, and these can lead to information gaps. Moreover, our measurements don't always have a direct relationship to the state of our system. And to make matters worse, in volcano studies, we lack this direct observation or confirmation on what is really happening beneath the ground. And of course, our observations always contain noise. Another way to extract information about the true state of the system is when we use models. Models are great because it allows us to have this quantitative and or qualitative understanding on how the system evolves and gives rise to observations. But we all know that all models are imperfect. And according here to George Fox, all models are wrong, but then some may be or are useful. So I guess the main motivation here is to be able to find this optimal solution or blend to combine our observations on one hand and our models on the other hand, as well as their respective errors. And to just boost the interest in this model data fusion strategy, I'd like to present this figure here. So here on the left-hand side is the ozone data captured on this 23rd of September 2002, and each point here has their own errors. And as you can observe also, the data is very sparse. Here on the right-hand side is a 6-day ozone model forecast. The figure here, or the colors in the figure here represents, the blue color here represents low ozone zone, whereas the red or the orange means relatively high ozone regions. And I would like you to notice this figure here. This is a result of combining observations and model. Here, the authors were able to capture the Antarctic ozone splitting in this region, which could not be revealed by just analyzing the data alone or by just looking at the model forecast. And this Antarctic ozone splitting was actually confirmed by other independent datasets. I'd like to just mention that in data assimilation community, the result of combining the observations and the model forecast is called the analysis. So in the next slides, what I want to do is to walk you through the mathematical basis of data assimilation. I will probably bore you a lot with equations. I am really sorry about that, but I just want to put us all in the same page. In particular, I will probably I will discuss sequential data assimilation approaches such as the ensemble Kalman filter and Kalman filter. And I will demonstrate some examples of sequential data assimilation and some provide some thoughts for this modeling collaboratory. So I will start by describing the physical system. The true state of the system mathematically can be described or be represented as X. It's a continuous state in space and in time, and it can be discretized using this operator to represent the numerical true state X dagger here. For the rest of the talk, when I mention about the truth or the true state of the system, I'm particularly just referring to the numerical true state of the system. The background estimate, which comes from the recent forecast or model simulation, can be written like this. So XB is the background estimate. It's equal to the sum of the numerical true state and some background error. The data or observations, on the other hand, can be written like this, wherein B is the data and it's equivalent to the product of the observation error and the numerical true state from plus some observation error. The observation operator is the link or the matrix that maps the numerical true state to your observation space. So remember, our goal is to combine all the pieces of information that we have and their relative uncertainties to obtain the best estimate of the state. And if we assume that the linear combination of the background estimate and the data is the best estimate, then we can write it in this form. So here XA is the best estimate. It's called the analysis. And if the observations and the background estimates or your model simulations have the same uncertainties, then obviously you can just take the average. But if, for example, your data has a better uncertainty than your model forecast, then what you want to do is to put more weight on your data. And how do we do this in a very objective way? Is again the million-dollar question. We want to find the coefficients alpha and beta such that we can obtain the best estimate of our system. So we can do this by assuming several things. First is that if we assume that the errors associated with your background estimate and your data are biased, mathematically, this means that the average of the errors are equal to 0. So the overline here means it's an average. And these errors should be uncorrelated. And again, mathematically, this could be represented as the mean of the product of the errors of the background estimate and data should be equal to 0. So if we follow these assumptions, then this linear equation just simplifies to the following equation here, with analysis variance equal to this equation. I will not go through the derivation of this one. I do not have enough time to show you how we derive these equations here. But what does this actually mean? If we take an example, a scalar case example, for example, if xb is equal to -2 with an uncertainty of 1, and if we set d or data equal to 2 with an uncertainty of 1, as I've said earlier, that they have the same uncertainties. So basically, you just average the values of xb and d. And in this particular case, -2 plus 2 over 2 is just 0. So your best estimate is 0. And the variance of this analysis is just equal to 0.5. Now, if we take another case wherein the background estimate variance of here, xb is higher. Now I put it in, I plug or I defined a variance of, or standard deviation of 2. If the background estimate variance is higher, then the tendency is that you could put more weight on your observation. And basically what this means is you trust the data more than the model simulation. And of course, this could work vice versa. So I've shown you an example for the scalar case, but this is not how we do it in practice. In practice, we deal with high dimensional problems. And the question is, how do we generalize this equation for large number of state variables and a vector of observations? And we can approach it by applying the Bayes theorem and using probability distribution functions to generalize the problem and represent our uncertainties. So Bayes theorem states that the posterior distribution of your state given the data is just equal to the product of your prior knowledge and your data likelihood over some scaling or normalization factor. So if we take the similar example from the scalar case, but now represent them as Gaussian PDFs, here the uncertainty of the prior is equivalent to the uncertainty of the data likelihood is the prior, and this is the likelihood function. If we multiply their PDFs, the product is the green curve here, posterior. And as you can see, as we've confirmed from the scalar case, your mean is at 0. Basically, you just take the average of the means of the prior and the likelihood because they have the same uncertainties. Now, if what happens when the uncertainty of the prior is greater than the uncertainty of the data likelihood? As you can see, you have a broader Gaussian PDF here representing larger errors. You see that the resulting posterior is not entirely equal to the observation, even though the observation has smaller uncertainty. Is because we still have, or we still consider having this information from the prior. But as you can see, its mean is now leaning towards the positive side because it basically put more weights or trust to our data because the data has a better uncertainty. And here I just want to note that the uncertainty of the posterior is always better than the uncertainties of either the prior or the likelihood function. So I want to point out that when applying Bayes theorem, you can use any PDF or distribution. But if we just assume Gaussian distributions for the error, then it becomes really easier and beautiful to write mathematically, particularly if we are dealing with high dimensional problems. And for that, we can generalize the equation using the multivariate Gaussian distribution equation. And for the prior, we can write it this way, and the likelihood function we can write it this way. And you see it's within an exponential function. And if we multiply the prior and the likelihood function, since they're within the exponential, it's basically just the sum of the brackets, the sum of the terms within the curly brackets here. So the posterior is just the sum of this one and this one. So to get a best estimate from the posterior probability, what we typically do is we take the maximum probability of our PDF, and this occurs, or we take the mode basically, and when you assume Gaussian distribution, the mode is just equal to me. This equation here is the one that we wanted to minimize, or the maximum probability occurs when when x minimizes, such that you have this cost function here. It's also called as the penalty function or your objective function. So there are several ways to minimize x. In practice, we can solve this using Kalman filter, using sequential data assimilation, for example. Or second is that you can use variational methods, but we will not talk about variational methods in this seminar or talk. I will just focus on Kalman filter. So the Kalman filter, if you assume that the model, the observation operator is linear, then this cost function just simplifies to this one. So this is your background state estimate, and you have this factor here, and this one is the difference between your data and your model forecast. So this factor, I would just simplify it to k, and in data assimilation, we call it as the Kalman gain. So Kalman gain is the magnitude of which your observation corrects the background estimate or your model forecast. So how do we practically implement the Kalman filter? We start by defining our state vector, xb. This state vector can be comprised of state variables. These are parameters that have direct link to the data. They can be directly corrected by the data. And sometimes you also want to infer uncertain model parameters, and these parameters doesn't have direct link to the data. So we will initialize the state vector and its error. And again, I just want to reiterate that XB is the background state estimate coming from previous forecast or your previous model or model simulation. Then if you have data or observation with defined uncertainty, you can calculate for the analysis using this equation here. So this is the mean values of your state variables, and this one is a way to compute for the covariance of the analysis state vector or the errors associated with your state variables. So the next step is to propagate the dynamical model forward in time to obtain the model forecast at t plus 1. And this is where dynamical models are really powerful, because if you are using kinematic models, you don't have this predictive capability, and you couldn't propagate the or you couldn't obtain a model forecast. You need this dynamical model to obtain your model forecast at the next time step. So similarly, after propagating the model forward in time, you can also propagate the uncertainties to obtain the covariance at t plus 1. And if there is no, or there are no observations at the next time step, then you can just again use your dynamical model to predict the next state of the system, as you can see here again. But if you have observations, then the process just repeats itself. You calculate for XA, you calculate for the covariance, and then you arrive at some analysis or prediction or corrected version of your state. So just some thoughts about the Kalman filter. So the Kalman filter directly solves this equation, but it's only valid for linear cases. The state covariance matrix P is, as you can see, updated sequentially as the system evolves here. But computing for P for high dimensional problems, even if the model is linear, is not really practical, because you can see here, this is PF and M is a model, your model operator. And if you have, for example, 1 million model variables or parameters, then it requires you to run this 1 million times, and it's really computationally expensive. So this is where the ensemble Kalman filter enters, and ENKF is based on generating certain number of models to approximate the mean and the covariance of the state vector. It's a Monte Carlo alternative route to address the nonlinearities of your model. And in ENKF, here you'll see that the initial model ensemble is forecasted towards time t, and this will result to the blue curve here, which is the evolution of the model covariance error PF. Then once observation is available here, the yellow curve here, which is the characterized by this covariance error here, the ensemble is updated with a new model covariance PA, and then the process iterates just again to the next step. So there are again several ways to implement the ensemble Kalman filter, but you have this stochastic ENKF approach and you have this deterministic ENKF. For this talk, I will just discuss the stochastic version, or we use the stochastic version. But in theory, what they really just do is to ensure that the ensemble that you produce is consistent with this equation here. So there are a lot of variants, deterministic way to approximate this equation here. For the stochastic approach, what we do is prior to the computation of the analysis or XA, we perturb the observations, and we use the noise coming from the distribution from your error, from your observation error distribution, which is this characterized by this term here. So again, how do we implement the ENKF? Similarly for the Kalman filter, you start by describing your state variables and or your model parameters. You put it into your state vector, and then use an a priori information derived from previous assimilation step or model simulation, and then initialize the data assimilation process. So we basically sample from this a priori information using some n number of models. Then we feed it to your dynamical model, and this will allow you to forecast the next state of the system and compute for the error covariance. Now, again, when observations are available, you feed them into your assimilation scheme, and you compute the Kalman gain, and then you compute for the analysis. And then the process repeats over and over again. If you do not have observations in the next time step, you can just use your dynamical model to predict the next state of the system. So of course, ENKF, or the ensemble Kalman filter, like any other technique, is not perfect at all. In weather forecasting, for example, they typically use 100 models, and this relatively small sampling size often leads to issues like ensemble collapse, wherein the state covariance matrix PF does not contain enough spread. Or second, you may have these spurious long-range correlations, meaning that, for example, in the weather here in California is spawn correlated to the weather in South Africa, for example. And to avoid these issues, there are several solutions proposed. So for the ensemble collapse, you just implement some covariance inflation. For the spurious long-range correlation, you apply some localization, basically just masking far field data points. So I hope I did not lose you. I hope I still have your attention. We are through with the introduction, and I should actually promise that it will get better, but maybe not. So please hang in there. Just some things to keep in mind. Any model can be used, but you need a model that will again best represent your system. And to leverage again on the potential of using sequential data assimilation, we need to use time evolving process-based or physics-based models, because again, if we use kinematic models, they do not have the predictive capability, so we'll lose this ability to forecast the next state of the system. Second is that you can use any data as long as you can link it to your model. And third is that we strictly follow Gaussian assumption for the observation and the background or model error to obtain the optimal or best estimate of the state. So in the next slides, I will show a demonstration by assimilating deformation measurements into a simple two-reservoir model. I will be using this two-chamber model of Reverso et al. Hélène talked about this model briefly in the previous talk, but I just want to add something about this description about this model. So this model is based on homogeneous isotropic elastic half space. You see that you have these two reservoirs connected by this hydraulic pipe here, and the bottom chamber or reservoir is fed by this magma inflow rate Q in. This model can actually explain the exponential trend followed by this kind of linear trend in the displacement time series during intereruptive periods. So the evolution of the overpressures within the shallow chamber and the deep reservoirs are given by these equations here, and I just rewrite it in a matrix form so that we have this kind of form of equation. And this is your model operator. This basically propagates your state vector forward in time. And this one is the equation for the overpressure displacement data relationship. So UR is radial displacement, UZ is vertical displacement. And again, I just rewrote it in a matrix form. And this one is H. So this is your observation operator, the operator that links your state vector to your data. So I just added a term for the line of sight displacement for insert here. That's why you have this third line. So in practice, when we do data assimilation, it's not really easy to just take this model and dump all your variables and parameters in the state vectors, especially the uncertain parameters. If we are doing state parameter data assimilation, it's not that easy. Uncertain parameters have no direct link to the data, as I've mentioned earlier, so they cannot be corrected directly, and they can only be, in fact, corrected by the covariance between them and the state variables. So to circumvent the issue of waiting for these parameters to stabilize in time, what we did during my PhD was to perform Bayesian inversion first prior to E and KF. And this is to fix non-evolving parameters first, such as the geometry of the reservoirs, the magma density contrast, and obtain a prior for the evolving parameters as input to data assimilation, because as I've earlier mentioned, we strictly follow Gaussian assumptions. And for Bayesian inversion, you're not constrained in using any other kind of probability distribution function. You can use a uniform one as prior information, and you can end up having a Gaussian form. So after performing Bayesian inversion to constrain our parameters or non-evolving parameters, then we're ready to do E and KF. And for that, we only follow or track the evolution of the state variables. For me, I would just track the evolution of the pressures and Q in, which is a parameter that may evolve or suddenly change in time. So for step one, for the Bayesian inversion, what you can do is you can use a priori information from independent data set. Or in my case, what we did is that we use an early subset of our data time series. and or invert the time series from the last intereruptive cycle. However, the problem for the second case is that volcanic sources can change from one cycle to another. So when we perform Bayesian inversion first, we can obtain this marginal probability of the uncertain parameters. And I can use these values as input to my forward model. And the result here is basically just the green curve. This is a synthetic case. The true value or the true behavior of the system is defined by the black broken line here. So this is the shallow overpressure as a function of time. And here is the evolution of magma inflow rate as a function of time. So it remained constant, and I was able to really track the actual behavior of the system with certain uncertainties. So this technique is not new and has been previously done by Kyle Anderson and Paul Siegel. They have applied it to Mount St. Helens using physics-based model and MCMC. As you can see here, they were able to use, for example, here the volume extruded and forecast it up to 4 years. So now I know that you wonder that if it's working well anyway with Bayesian inversion like MCMC, why do we still need to do sequential data assimilation? First is that when we apply sequential data assimilation, we do not need to invert for the whole time series. We can basically just follow the evolution of the system in quasi-real time. As you can see here, we do it in a near real-time approach. Second is that when one of your parameters or your uncertain parameter, in my case here, Qin, suddenly change in time, then you can track this transient behavior. And we've done this for the 2005 and 2005 to 2018 intereruptive period at Sierra Negra volcano in Ecuador. So this is the vertical displacement time series, and this is cumulative displacement from INSAR. This is the overpressure as a function of time, and this is the Qin bottom influx rate as a function of time again. So we note here the Cerro Azul May 2008 eruption that occurred in this period, and then the Cerro Azul March 2017 period, March 27 intrusion that occurred in this period. As you can see, the vertical displacement ramped up just after this intrusion event, and we thought that we associated this ramping up of the vertical displacement to a rapid increase in the value of the bottom magma influx rate. So you can see here. We also applied this to the 2011-2014 intereruptive period at Grimsville volcano. Here it's a very special case because in 2014 August 2014 was the Barabunga Polaron eruption. So this is the radial displacement as a function of time. And again, I'm plotting here Qin as a function of time. And what we've found out by using sequential data assimilation is that we were able to track this decreasing trend or supply of magma into Grimsvot's volcanic system. And we thought, or we interpreted this missing volume of magma into two kind of scenario. First, that this volume of magma may have laterally transported to Barabunga and affected its system, or this volume, this missing volume may have been a consequence of some kind of magma surge towards Barabunga. That's why you're losing kind of this supply into Grimsvot magma plumbing system. So another interest or reason why we should perform sequential data assimilation is that we can assess the state of the system at each time step. So Hélène has discussed about assessing the stability of magma reservoir or chamber using more column in previous talk, but you can also use overpressure criterion. Here in this particular case, what we did is we hindcasted the 2004 to 2011 period at Grimsvötn volcano in Iceland. We defined a failure criterion distribution, as you can see here, and here we assigned each of our models their failure criterion at time t equal to 0, and this was drawn from this distribution. And at each time step, what we did is we evaluated how many of these models have actually exceeded their initially assigned failure criterion. So here is the shallow overpressure, just a function of time, and red is the result of data assimilation, and green curve is basically just forecasting the model forward in time for several time steps. So this plot here, this is the plot of the number of models that exceeded the initially assigned failure criterion over the total number of ensemble. So when we use this kind of approach, we were able to derive this plot here. So this is the forecast day of eruption as a function of time, and this is days left to eruption day. These two plots here are just the Zoom versions 2 weeks prior to the 2011 eruption of Grimsvötn. And again, this plot here is just a plot of the number of models that exceeded their initially assigned failure criterion over the total number of ensemble. And as you can see, because this is hindcasting, it really worked well in our case for the 2004 to 2011 intereruptive period of Grimsvötn. Patricia Gregg's group in Illinois are also developing this kind of ENKF frameworks, but they are rather using finite, more realistic models like finite element models. They've been recently successful in hindcasting the 2008 eruption of Okmok, and here in this particular case, this is a work led by John Albright. They evaluated how many models at each time step are in tensile failure by using using various tensile strength criterion. So in this work, an ensemble model member is considered to be in failure if the tensile strength or stress exceeds the given tensile strength values. And here, regardless of the strength values that they use, their models are in tensile failure in 2008 or just before the eruption of Okmok. So indeed, the framework that I have shown here is just based on simple time evolving physics-based model with really very simple assumptions. And this is, or this may not hold true for other volcanic systems. We should, again, indeed, explore more realistic cases, adding complexities into our model. However, we should also keep in mind that as we complicate things, there are computational costs to consider, especially when we talk about real-time eruption forecasting. Hélène have initially or previously shown how ambiguous the interpretations can be when we only use deformation data. So in terms of eruption or operational eruption forecasting, there are still a lot of things that we should discuss as a community. And I believe that the framework or strategy that I have just shown here is a very small part of the bigger picture when it comes to forecasting eruptions. So Mike will talk more or will detail this Bayesian decision tree on Thursday, but basically in this Bayesian decision tree, each node here, the circle ones, correspond to a decision node. And for me, the two-chamber model that I've shown you in combination with ENKF will fit into this part of this Bayesian tree. And this will help us decide whether the unrest could lead to an intrusion or to a magmatic eruption, again, under some threshold criterion value. or assumption. So once eruption has initiated, we can just shift into another model or use another model, and then we can still apply the concept of ensemble-based data assimilation. For example, here in this case, they use full 3D plus ensemble transform Kalman filter. It's a deterministic ENKF. They applied it for the 2018 Mount Etna explosive eruption. So this is the observation from Severi satellite, and this, I guess, so this is the model forecast, and this is the analysis. So top to bottom is just the evolution of the ash cloud trajectory. So for me, I would say that data assimilation is the perfect chef that mixes the right amount of ingredients to obtain our best tasting food. It's either your mother or your grandmother, whoever cooks the best food, right? But kidding aside, data assimilation is currently an operational approach used in numerical weather prediction centers. It's not a new technique, but this field or approach remains very new in volcanology. As I've shown here, it has a lot of potential and probably big promises in terms of tracking the state of our volcanic system, and more importantly, in terms of eruption forecasting. It provides, or it is an efficient framework that allows us to combine our imperfect model and our erroneous data to estimate the state of our system under really strong Gaussian assumptions. Just want to emphasize that when you use models, you can't go too wrong with your model. You still need to have a good understanding of your system. You have to know your system dynamics, the physical properties, and be able to define their uncertainties. Finally, I think it has all long been recognized that we need to combine diverse data sets and time-evolving physics-based models. But I guess I just want to reiterate that we really need to start putting it into practice. Hélène showed how ambiguities again arise when you only use data to constrain your models. And I will leave you with this slide here. This is the work of Ying-Chi Wong and Paul Siegel, published recently. And I really like this model because they combine the extruded, or this paper or work, because they have combined the extruded volume, deformation, and CO2 emission time series, and apply it for the 2004 to 2011 eruption of Mount St. Helens. So thank you very much, and I am ready to take questions.
So we have one question in the chat box from Clifford Thurber. He asks, it looks like you have a negative bottom influx rate for a period of time. Is it real? If yes, what is causing it? If no, can you use a non-negative solver to avoid it?
Well, so for that, I think you are pertaining to the Sierra Negra, right? So I do not constrain. Yeah, so it's true. You have negative queuing value for that. It may be unphysical, but some people have explained that you could have this backflow in terms of interpreting that kind of signal. But in my case, when I applied ENK for that, I just allowed it to fall into negative value. And but in theory, you can also apply some resampling technique to avoid those kind of unphysical values of your parameters.
Great. Next question is from Santiago Ariano. Thanks for the nice talk. What is the main risk of using this approach if we know that errors are not normally distributed?
Well, basically, you won't get the optimal solution, right? Because you just don't assume Gaussian errors, and this strategy was based on those strong Gaussian assumptions.
We have the next question from Leif Karlström. Grace, one difference between volcanic systems and weather prediction is the uncertainty in equations to solve. How do we address this in the framework you describe?
Yeah, so that is very difficult to define. So there are, in fact, in numerical or in weather forecasting, it's a totally new field to identify or describe this model error. It could be based on some simulation. And in fact, for volcano applications, I do not really exactly know the answer, but what you can do is also add some, perturb some of the parameters that you are uncertain, such as, for example, you could use some elastic distribution for your Young's modulus, those things, I would say.
Yeah, I guess, one of the things that struck me about this compared to or contrasting with Helene's talk, which was also great, is, of course, there's a wide variety of processes that are described. And it's not totally clear to me that you'd be able to uniquely determine which ones are relevant with the data we have. So I guess, yeah, I'm a little unsure about the path forward in this approach.
I think so. I think what we can do is basically set up our model based on what we know about the volcanic, the particular volcanic system. I'm not sure if you can use one general equation for this one. You really have to how do you say really focus on developing a unique model for a certain volcano in order for this thing to work. Because as you've seen, or if you only use deformation data or displacement data, there are a large amount of reasons or explanation to explain the deformation that you see, and there are a lot of processes that could be associated with the deformation. So I guess the first step is to use geology, use all the a priori information that you can do to set up the model, develop that model, and be able to plug it in data assimilation frameworks like this. But for some systems, like for example, basaltic volcanoes such as Sierra Negra, Grimswood, those are frequently erupting ones, and those with really strong deformation signals, it could work, I guess. But in terms of operational approach, I'm not confident that we're there yet.
All right, with that, it is 1:30, so I think we'll go ahead and wrap up. Thanks to everyone for your attention today and interest in the MCS, to our moderators, Sarah and Adrian, and in particular to our speakers, Helen and Grace, for their really great talks today. As a reminder, our next webinar will be this Thursday, same time and place, and also focused on integrative volcano modeling and forecasting. Our speakers will be Mike Poland from the USGS and Paul Siegel from Stanford. As Helga mentioned early on, finally, of course, these workshops are building towards an ultimate report, which is going to be part of the MCS report. And to that end, on Friday at noon Central in the US, we're going to have a planning meeting focused on how a modern collaboratory can be used to address some of the science questions raised today and on Thursday. So this is our opportunity to really have a more in-depth discussion. Everyone is welcome. You do have to register separately, so please go ahead and sign up online. With that, again, thanks everyone, and hope to see you on Thursday.